1. Hi everyone, welcome back to another Planetarium live stream. My name is Jessica, I am the director of the Planetarium, and with me tonight are two of our students who I will let introduce themselves. And we'll start with Lindsay to my left.
Hi, I'm Lindsay. I'm a physics graduate student at UMD.
And I'm Eli. I'm a physics undergraduate student at UMD.
So tonight, Lindsay and Eli are going to take you on a journey as we explore just how big our universe actually is and some of the really strange and awesome things that we can find in it. Now, before I hand it over to them, if you do have any questions for us tonight, leave them down in the comments. I'll be watching those throughout the show, and we'll let Lindsay and Eli know when they come up. Otherwise, we will also have time at the end to answer questions as well. So with that, I'm going to just turn it on over to, I think, Eli, you're starting us off.
Yep. So give me just a moment here to make sure I get the right window up. Okay, does that look right? Oh, but we do actually want to go back to slide 1, I think. Boom. Okay. So here we go. The way I wanted to structure it was start with really small stuff and then build up to bigger things based on how small the other stuff was. So we'll start really small with the proton, which is a subatomic particle. And is the window still up, right? Because my window kind of tapped it down. Okay, cool. Subatomic particle that is found in the nucleus of atoms, along with neutrons and electrons. And its diameter is 1 × 10⁻15 meters. So I wrote out all these numbers. I usually try not to have a ton of text on slides, but I wanted these numbers to be visible. So that's how it is that many meters in diameter. And neutrons are similar in size. So just for reference, 5.3 × 10⁻17 protons, or that number you can see below, lined up like tip to tail, is how many would fit at the tip of a needle. So they're extremely small, and it's kind of crazy to think about how many of them are like around you in all the atoms and stuff. Also, there's even smaller stuff. Protons and neutrons are built of these smaller particles called quarks. And they're about 1 × 10⁻18 meters. We don't have like a super firm number on those, but they're extremely small, much, much smaller than protons. And electrons we can't really give a number on because we can't really see them. Like this picture says here, you can't pick one out as like in one spot around the nucleus of an atom. They're in this like cloud of probability. So we can't really talk about the size of electrons. So the smallest we'll go is with the quarks. Again, extremely small. So I really like using this reference to give an idea of how small atoms really are. So if you had a football stadium, the nucleus of the atom, which like for a hydrogen atom is just 1 proton, would just be the size of a pea in the center of that huge football stadium. So it's kind of crazy to think about that scale and how much of an atom is actually empty space. So now we'll talk about life and the smallest life that we know of. So the smallest viruses are somewhere in the range of 20 to 400 nanometers. And E. coli bacteria is 2 × 10⁻6 meters, or 2 micrometers. And that would be 2 billion protons lined up tip to tail to be 1 E. coli bacterium. So extremely small. And that's the colony is reproducing. That's an E. coli colony. Down on the bottom right. So that first one that you see that it starts from would be 2 billion protons lined up, which is kind of crazy to think about. So now we can start looking at some bigger life. So the height of an average human male is 1.75 meters tall, and that would be 875,000 E. coli bacterium lined up, which would be 1.75 × 10⁻15 protons lined up, which is just an unfathomable number. And the largest known animal, which is the blue whale, is 33 meters long, which would be 19 human males. So 19 × 875,000 is how many E. coli lined up would equal a blue whale. So it's already starting to get kind of hard to grasp these numbers. So the biggest object created by humans is this tower right here, the Burj Khalifa, which is 829.8 meters tall. That would be 25 blue whales stacked up, which is incredible that they're that big, and 477 human males, 478 almost, standing one on top of the head of the previous one to reach the top of that, which is just insane. And 4.18 times 10 to the 8 E. coli bacteria. So, like I said, numbers are getting really hard to keep up with. So I'm just going to build off of the smaller stuff that we talked about previously for scale now. Mount Everest is 8,848 meters from ground level to the peak. That would be 10 and a half of that tower we talked about last slide, or 264 blue whales, or 5,000 and about 18 human males standing up like that, which is crazy. And then we go to Earth. Diameter is just under 8,000 miles, which is just over 12,000 kilometers, or just about 12,500. And that would be 1,440 Mount Everests stacked on top of one another, or 15,121 of that tower, the Burj Khalifa, or 380,294 blue whales. So already astronomically, when we're only looking at the Earth, it's kind of hard to find a good reference point. So the next thing I wanted to include, because there's a really cool fact about it, is the distance from the Earth to the Moon. 31 Earths would fit in between the Earth and the Moon, which turns out to be about 44,640 Mount Everests, or just under 500,000 of that tower, the Burj Khalifa. And a really interesting fact about this distance is that all of the planets in the solar system would be able to fit in between Earth and the Moon, and it would be kind of snug, but there'd be a little bit of breathing room, but not much. And I think that's a pretty incredible fact, that all of those planets could fit in there. So now we'll talk about kind of distances in the solar system. So these numbers start to get huge. Obviously, the distance from the closest planet to the sun, Mercury, to the sun is still 35.98 million miles. And just for reference, that's about 151 times the distance from the Earth to the Moon, which would be about 4,600 Earths stacked up tip to tail. So just kind of a general rule of thumb with the planets that you can rely on is that each planet is about 1.5 to 2 times as far from the sun as the previous planet, except for Jupiter, because there's a really big gap in between Mars and Jupiter. But each planet in the terrestrial planets and the Jovian planets is about 1.5 to 2 times as far from the sun as the planet before it. So the outermost planet, Neptune, is about 11,000 times, almost 12,000 times the distance from the Earth to the Moon from the sun, which for reference would be 362,491 Earths stacked next to each other to span that distance. Okay, so we need to take a detour for a second and talk about a new way to give distances, because Earth to the Moon distances are going to become ineffective really fast. We're going to talk about light years and light speed. So light travels at 300,000 meters per second. And just for reference, that means that 8 minutes is the time it takes for light to get from the surface of the sun to the Earth. And that turns into 4 hours when you're going to Neptune. So the light year is just how far light travels in years. So that's 300,000 meters per second times the seconds in a year, pretty much. And that turns out to be, I believe that's 9 trillion meters. 9 trillion. It could be quadrillion. I don't have it typed out, but that number right there is how far it moves in a year. So now that we have that benchmark to go off of, we'll talk about nebulae, which are just really big clouds of gas and dust that are sprinkled throughout the galaxy. And they act as really good nurseries for stars, but also graveyards, because when a star dies, it puffs off all that gas, and then later on that gas can turn into another star. And on average, they vary in size a lot, but they're about 0.85 light years in diameter. That's just the average number. Which would be 600 solar systems of width. So they're absolutely massive. But they look fantastic when you look at them from the outside. But when you're in them, they don't quite look like that. They're really thin. So it would be a pretty much empty space, but a massive region of empty space. Now we'll talk about the nearest star, which is called Proxima Centauri. It is 4.12 light years away, which means that when we see that star through our telescopes or whatever, it means that that light took 4.12 years to get from there to us. And just for reference for how far 4.12 light years away is, that is 264,000 times the distance from the sun to the Earth. So 264,000 of those spans is about the distance to the nearest star. So incredibly far away, even though that's our closest neighbor. So next we'll talk about the Milky Way. It's about 100,000 light years in diameter, which means that light takes 100,000 years to travel from end to end, which is kind of scary in itself. And it has this supermassive black hole at the center, which is 27.5 million miles in diameter, which is just about, if you place the black hole where the sun is, it would reach Mercury, just about. And it's really heavy, 4 million solar masses. So it's worthy of the title supermassive black hole. But it's kind of weird to me to think that that much mass can be packed into a size of just the sun to Mercury, but I suppose that's kind of the whole deal with black holes, so I shouldn't be too surprised. So the Milky Way diameter, 100,000 light years, is about 6.5 billion times the distance from the sun to the Earth, which is about 25,000 times the distance from us to the nearest star. So pretty big. And now we get to the next galaxy, the Andromeda Galaxy, which is our closest neighbor galaxy. It is 2.5 million light years away. And that means that light that comes from that galaxy is 2.5 million years old by the time it reaches us. So we're really seeing that galaxy in the past, which is kind of cool to think about. And it is about 25 Milky Ways away. So if you stack the Milky Way up tip to tail 25 times, that's about how far away it is, which is 625,000 times the distance from the sun to the nearest star. And a cool fact about the Andromeda Galaxy is the Milky Way and the Andromeda Galaxy are kind of on a collision course. So in about 4 billion years, our galaxies are going to start to mesh together. And I really wish I could be there for that, because we're actually just going to have a huge galaxy in our night sky, which is going to be really cool to see. And next, we'll talk about the local group. This is just kind of a region of space around the Milky Way that is just kind of a nice, concise group of galaxies and dwarf galaxies. So the distance from the Milky Way to the Andromeda Galaxy is about 1/4 the size of the local group. And it's roughly defined, but about 125 Milky Ways lined up would be how far it is across. And that would be 78 million times the distance from us to the nearest star. So quite large. And the Andromeda and Milky Way are the two largest galaxies of the group. And the local group is part of something called the Virgo Supercluster. And it's just this large filamental kind of web of galaxies dispersed in this area. And it has a lot of voids in it, and we'll talk about that in the next slide, I believe. It's about 110 million light years in diameter, and it's actually a part of an even bigger structure called Laniakea, which is kind of like another iteration of the filamental structure, and the Virgo Supercluster is just a part of that. Oh, maybe we won't talk about. Oh no, voids are what Lindsay's going to talk about, I believe. And now looking at the observable universe, it's about 27.54 billion light years across. But that is just the observable universe. We have no reason to believe that there's not more universe out there, but we can only see so much because light has only had so much time to get to us from further out. So it's growing every second. We see more, but it's quite large. It would take a lot of time to get from one end to the other, more time than you or anyone will ever have. So absolutely massive. And now we're going to move on to some of the cool stuff that's out there, and Lindsay is going to talk about this. So I'm going to stop sharing my screen.
All right, so we are going to talk about some of the wonders of the solar system now. So neutron stars are something that can happen when a star dies. So in this case, it's a very, very massive star. Could be, for example, 1,000,000 kilometers wide. A star that big, when it dies, is going to die in a supernova explosion. And then the leftovers are going to collapse. The leftover of the star is going to collapse into a very tiny neutron star. It can be as small as 20 kilometers. So we take a star 1,000,000 kilometers wide, and now we have this really compact, dense star that's 20 kilometers wide. And it's called a neutron star because it is made of neutrons. Not super creative name. But something that is really cool about neutron stars, so it takes pretty powerful gravity to kind of make a star this tiny and this dense and this compact. If you dropped a marshmallow on the star, it would hit with an impact of 1,000 nuclear bombs. So even really tiny things falling on the surface of this neutron star can have a big impact. Now, sometimes neutron stars are rotating, and then they are called pulsars. So all pulsars are neutron stars, but not all neutron stars are pulsating. So this pulsar, what's happening is it is rotating. And some pulsars actually rotate 716 times per second. So that's pretty amazing. This 20-kilometer wide neutron star is now rotating at 716 pulses per second. And these beams that are coming off the pulsar, those are high energy beams that are kind of lined up with the north and south magnetic poles of the pulsar. And so then we call it a pulsar because as it's rotating, it kind of seems to be pulsing at us. Another cool thing out there in the universe is ring galaxies. And one thing or what makes them cool is just they're very mysterious. We really don't know how these ring galaxies form. So outside of the ring galaxy, you can see that there are a lot of blue stars. And then the central part of these ring galaxies are more white. So when you see an area in the universe, like in a galaxy or a star cluster or something, and you see a lot of blue stars, that actually means that that's a little bit of a younger area, because blue stars are really big and really hot, so they burn through their fuel really fast. So places that have blue stars aren't that old yet because those blue stars haven't burned through their fuel yet. So in the center, it's whitish because we have white and red stars left over. They live longer than blue stars. And so the center is older than the outer ring. A couple of different ways that these maybe could have formed is that maybe there were two galaxies at one point, like maybe the older stars were one galaxy and the younger stars were another galaxy, and then they just kind of merged into this ring-like galaxy. Another idea is that there's just based on like the gravity distribution of the ring galaxy, there are no stars that can maintain an orbit in this area, this space between the middle and the outside ring. And so any stars that were there or are there kind of get kicked out of that space. Another idea is that the central part of the ring galaxy maybe formed first, and then somehow the ring formed later after it, but they are this part of the same galaxy. So it's just a really strange object out there in space, and the fact that, you know, it has this ring and then this space with no stars, and then this central area. Okay, so Eli talked a little bit about galaxy clusters. So when the Big Bang happened, everything was kind of, all the matter was kind of distributed evenly. Well, areas that had a little bit more mass pulled in matter closer to that area. And so that area gets more massive and more massive and more massive and keeps pulling in matter. And then it leaves some spots in the universe kind of empty. So matter, because of gravity, these spots in the universe that have more matter just keep attracting more and more matter towards them, leaving these blank voids. And the voids can be as big as 100 megaparsecs. So we're not even using, even the unit light year gets pretty useless at this point. Here it says 100 million light years. That is about 1 megaparsec. Okay, black holes. So we talked about neutron stars earlier, and they happen after a very large star, supernovas. But stars that supernova don't always form a neutron star. If that neutron star and what's left over after the supernova is bigger than 3 solar masses, its gravity is going to be so great that it's going to continue to collapse and it's going to become a black hole. Remember, you know, just a tiny marshmallow on that neutron star could have the impact of 1,000 nuclear bombs. So that really high gravity, it gets too much over 3 solar masses, collapses into a black hole, and they are black because light cannot escape the black hole. So light is going at such a speed that it cannot go fast enough to escape the gravity of the black hole. And so this area is black. When we're looking at other stars out there in the universe, we see them because they're emitting light, and light is coming to us from them. But the black hole, its gravity is just too big, and it can't, and so the light can't escape. Sometimes black holes have an accretion disk around them, which makes it a little bit easier to find them. But in this case, we have an actual image of a black hole that a team put together. I think it was about a year ago now. I think this is M87. One of my favorite things out there in the universe are exoplanets. So exoplanets are planets around other stars. There's a few different ways that we find them. This way is kind of the most popular way. So you have a star, and it's emitting light at a certain brightness. And then when the planet starts to cross in front of the star, some of that light gets blocked out, and so the brightness dips down. You know, the star is too far away and the planet's too small to actually be able to see a picture like this with a planet crossing in front of the star. For the most part, the planets are too small to be able to do that. So we look for changes in brightness with the stars. And we found about, I think, over 4,000 exoplanets now, which is pretty cool because I think the first exoplanet was found in the 90s, and already we found over 4,000 of them. And there are some stars actually up in the sky that you don't need a telescope to see. You can just see with your naked eye, that have exoplanets around them. So here's the Big Dipper. So if you are able to find that pretty easily outside in the sky, then we follow over here to the nose of Ursa Major, the Big Bear, that star, Mosita, and it has an exoplanet around it. So when you look at that star, you will know you're not just looking at a star, but you're also looking at some planets. Another star, this one is even easier to spot. It's a red star in the constellation of Taurus. It's up in the winter, so it's not quite up yet. But once Orion is up in the night sky, you just take the belt of Orion, takes you right to this bright red star in Taurus. So yeah, this star also has exoplanets around it. So another star to look at and know that you're also looking at planets and maybe some aliens. That would be pretty cool. And then also kind of up in the winter, here's Orion's belt again, Aldebaran that we just looked at. And then we have the Gemini twins. Castor is the star, Pollux is right below it. Pollux is another star that you can look at with your naked eye that has planets around it. And then this is Leo the Lion. So here's Leo's mane, the bright star in Leo the Lion, Regulus. So if you just kind of hop up this backwards question mark shape to this star right here, Algebra, that is another place where there are exoplanets around that star. And kind of a fun fact about some of these stars, their names are kind of unique, right? Aldebaran, Lucida, Algebra, and our last one is Kochab. Those are actually Arabic names. So the Arabs actually adopted the Greek constellations. That's why we still have the Greek constellations. But the Greeks didn't really name very many of the stars. And so all of these stars are actually, were named by the Arabs. So this last one here is the Big Dipper again. So we're back in the north. And then here's the Little Dipper. So this corner of the cup of the Little Dipper, Kochab, another star that you can look at in the night sky pretty easily that has an exoplanet around it. You won't be able to see the exoplanet. It'll be too small and too far away, but you will know that you are looking at one.
Awesome. Well, Lindsay, we did get a question about the ring galaxies. From Honor, she asked, can it be assumed or theorized that the ring galaxies are moving away from a center in the same way that other galaxies are moving outward, like the expanding universe? Something weird happened that created the void between the center and the ring, some type of cosmic event we cannot yet understand. And then she also wants to know, how does gravity affect the ring galaxies? So a bit there. So I don't know how you want to take that. I guess I would probably say we should start by saying that galaxies themselves are not affected by the expansion of the universe. The expansion is not strong enough to overcome the gravity in galaxies or even in galaxy clusters or groups. It's more that the groups of galaxies are moving apart from each other. So like those voids are getting bigger and bigger. But I will turn the rest over to Lindsay because think she knows more about the ring galaxies than I do.
Yeah, so there definitely could be some process that we don't even know about yet that formed these galaxies. And I think there's still a lot unknown. I think there's some research going on right now trying to measure the gravity of the center part and the outside part, and also like the amount of mass in those two parts. So yeah, we don't actually know quite yet what's going on with the gravity in those galaxies.
Which I'll also say is one of my I say one of the great things about astronomy is it's still a very active field, meaning there's still a lot of questions, there's still a lot of research going on. There are new things we're finding every day, which keeps our job interesting. All right, well, that is the only question I see right now. If you do have any other questions for us, please leave them down in the comments, and we will get those answered for you. But while I give a few minutes for questions to come in, if there are any more, let me tell you a little bit about what's coming up over this next week. So next week is going to be basically Moon Week. On Wednesday, we are doing a show, Moon 101, a crash course on the moon. We're going to tell you all sorts of fun facts about it, information about how it formed, the geology, which I know our geology queen, Lindsay, is going to be taking on that. And it's going to be a lot of fun. And this is all leading up to our event next Saturday, our socially distant stellar Saturday. That is going to be all about you becoming a lunar explorer. We're going to be handing out these activity kits with lots of fun activities all themed around the moon that you can come and pick up. We will also be raffling off a book about the moon, and we'll post more about that on our Facebook page on Monday. If you are interested in purchasing one of the Stellar Distancing t-shirts, you can pick those up that day as well. And we're also going to be doing a really fun moon crater activity with water balloons. I mean, who doesn't love throwing water balloons, right? And then that evening is International Observe the Moon Night, and so we will have a telescope stream on the moon and also be around to answer questions. And yeah, that's what's coming up over the next week. Oh, we got another question. Do you have any tips for finding the little, I'm assuming you mean Little Dipper, in the sky? We always struggle to locate it.
Yes. Well, it's a little bit misleading because the Little Dipper is kind of famous like the Big Dipper, but it's a lot more difficult to see, especially if you're living in an area with light pollution. Most of the stars are pretty dim. When I'm here in Duluth, I can usually only see the North Star and then 1 or 2 stars at the end of the cup of the Little Dipper. But yeah, that's normal, that you can't see it very well unless you get into a really dark place.
Yeah, and I am pulling up Stellarium real quick so that I can show you the very quick tip that we always use to help you find it. So whoops, my computer is not happy with me right now. There we go. Okay, let me get switched over. All right. So the tip or the trick to help you find, or at least find the North Star, is to first find the Big Dipper, which is usually easy to find, even with light pollution. Those stars are very bright and can usually be seen. And then what you're going to do is take those front 2 stars in the cup of the Big Dipper. These are our pointer stars, because if you connect them in a line, they will point you to Polaris, the North Star, which is the end of the handle of the Little Dipper here. And usually all you're going to see of the Little Dipper is Polaris and these front 2 stars of the cup, because those are the brightest 3. The others are a lot more difficult to see, as Lindsay was saying. And
Jab that I mentioned has an exoplanet around.
Yes. But that's the trick to finding it. And yeah, you probably won't see the entire Little Dipper unless you're in super, super dark skies. I also was going to say, if you are interested in learning more about the exoplanets that Lindsay talked about, we did an entire show about this a few weeks ago. You can find that on our YouTube channel or in the videos section of our Facebook page, where we have all of our past live streams archived. So we've done all of that if you want to learn more about that. But yeah, I am not seeing any more questions come in. So I think we will wrap it up there. Thank you, everyone, for joining us tonight. We hope you enjoyed your show, and we also hope to see you at our socially distant Stellar Saturday next week. We do ask that you please wear a mask and follow all protocol just to keep the community and our staff safe. We'll have details posted about directions to walk and where to park and things like that. And yeah, I think that's it. I think that's everything I need to say. So thank you again. We hope to see you next time. Have a wonderful rest of your night and a wonderful rest of your weekend. Bye, everyone.